Hello everyone, welcome to another episode of Coding Adventures. Today I'd like to experiment with ray tracing. Now, I have actually done some super simple ray tracing before, but it wasn't the main focus of the video, so I really didn't even scratch the surface. Later on, I also played around a bunch with the related idea of ray matching, so I have at least a vague idea of what's in store for us today, but I'd still like to start out with a bit of research. So I've been reading through this thrilling ray tracing in one weekend trilogy, accompanied by a great series of blog posts titled Casual Shader Toy Path Tracing. And now, with a bunch of new ideas floating around my head, I'm excited to get started. I'm going to be building this inside of a game engine, just for the convenience of having this little scene view set up for us, where we can place objects and move them around and so on. What's also nice about this is that we'll be able to easily compare how things look out of the box with this built-in renderer versus our fancy ray-traced renders. For the comparison to work though, we'll need to make sure that we render things with the same perspective as this game camera here. So I've written some code quickly to make sure I understand how the camera is set up, and that just draws this grid of points on the projection plane. So if we change the field of view, for example, we can see our points updating correctly along with it. And of course, if we move the camera around or rotate it, we can see that it works perfectly as well. So here's the code for this. We start by calculating the height of the projection plane using the field of view and some trigonometry, and the width follows from the aspect ratio of the display. Using that information, we then calculate a grid of points, and each of those points is transformed to respect the position and orientation of the camera. What we can now do is calculate the direction towards each of these points from the camera, and let's just draw some little arrows to visualize that. So these represent the rays that we're going to be shooting out into the world in order to figure out what we should be able to see. This might seem a little back to front, since of course we know that in reality light is emitted from sources like the sun, then bounces around off various objects, and whatever makes it into the camera or our eyes is what's visible to us. Problematically though, the vast majority of that light will miss our eyes, making this approach wildly inefficient. So that's why we're going to do things ancient Greek style, and shoot the light beams out of our eyes instead. Only the rays that actually end up at a light source can contribute to the image, but it's still a lot less wasteful than what reality is doing. Alright, now we're going to want to send out millions of these rays, which sounds like a job for the GPU. So I've written this ray tracing manager script, and all it really does is send that camera information we figured out to a shader that we're going to be writing in a moment, and then it runs that shader and draws the result to the screen. So all that's left to do is write the shader. Whatever we put in here is going to be drawn to every pixel on the screen. So for example, if we return the color red, we get a red screen. One vital piece of information we have though is the coordinate of the current pixel. So if we return the x-coordinate, we get a gradient from 0 on the left edge to 1 on the right edge, and if we return the y-coordinate instead, then obviously the gradient will be vertical. Okay, I've added some code now that uses those coordinates, along with the camera info we supplied, to just calculate the position of the current pixel on the camera's projection plane. And I'm doing it with a matrix multiplication this time, but it's essentially the same thing we did earlier. Then I've also added a ray structure up here, which just holds an origin point and a direction. So the origin will be the camera position, which is given to the shader by default, and then the direction is just like we calculated before. Let's then quickly visualize this direction as a color, just to make sure that it looks correct. So I'll enable the shader in the scene view, and now we're expecting to see XYZ correspond to RGB. So if we look along the positive X direction, we should see things getting more red, which they do. Then if we look up along the Y-axis, we should see things becoming more green. And we already saw that looking forward along the Z-axis, we have a lot of blue. We can also look behind us, and we should see this one octant here where all three axes are negative is just a black void. Everything checks out, so let's take our next baby step and try drawing these spheres. Like most 3D graphics, these are made up of triangles, which we'll definitely be tackling later on, but for such a simple shape we can be a lot more accurate and efficient with a pure mathematical representation. So the equation for a sphere centered at 0 is x squared plus y squared plus z squared equals the radius squared. To figure out if a ray intersects the sphere then, we can say that we start at the ray origin and move along the ray direction for some distance. When the squared length of that vector equals the squared radius of the sphere, we've hit the sphere. Solving for distance, we end up with this equation, and if the part under the square root is negative, then the equation has no real solution, meaning the ray has missed the sphere. If it's 0, however, that means the ray touches the sphere at just one point, and if it's positive, that means that there are 2 points where the ray intersects the sphere. So in the code, I've created this hit info structure to tell us, first of all, whether the ray did actually hit something, and if so, the distance, position, and normal vector of the hit. For anyone unfamiliar, the normal vector just means if you were standing on the surface, what direction would be up, which is going to be helpful when we try to figure out how the ray should bounce off the surface. Anyway, here is the sphere intersection code which computes all of that. And by the way, to handle spheres with different positions, we can conceptually keep the sphere centered at 0 and just move the ray away instead. Okay, let's quickly edit our shader to check if the ray hits a sphere at the center of the scene with a radius of 1, and return white or black depending on that. Then we can go see what that looks like, and it seems pretty spherical. So for our next step, I'd like to handle multiple spheres and have them automatically match up with the ones we've placed in the scene view. So I've created 2 new structures. There's a ray tracing material, which currently just describes the color of an object, but I'm sure we'll find more things to put in there later. And there's also a sphere structure, which just holds a position, radius, and material. This information about the spheres in the scene will get sent over to the shader and end up in this buffer over here, which is then used by this little ray collision function to figure out which sphere the ray will actually hit. All this does is loop over every sphere and perform our intersection test. Then if it hits the sphere, it checks to see if this is the closest thing that's been hit so far, and keeps track of the hit information if it is, along with now the material of the object as well. So we can then replace that single sphere test we did here with our new ray collision function, and return the color of whatever it hits. Okay, let's head back to the scene, and we should now be able to see all 3 spheres in their correct places. I'm also going to try setting some colors quickly, just to make sure that that works. And let's also look around a bit, because I want to make sure that nearby things are appearing properly in front of distant things, and that does seem to be behaving. So our next goal is to take these bland balls and make them more interesting looking with some actual lighting. To begin with, let's think about what we want to happen when a ray of light hits a surface. Obviously, that's going to depend on the type of material. If it's really smooth, for example, the ray might bounce off it like this, with the same angle going out as it had coming in, which is called a specular reflection. But if the material is more rough, the incoming light could potentially scatter out in any direction, which is known as a diffuse reflection. Let's focus on that kind for now. So when our ray hits a surface, we want it to just bounce off completely randomly. I've started making this little test shader to just figure out how we're going to handle random numbers, and so far I've just calculated this pixel index, which is a value from 0 up to the total number of pixels in the display. So if we visualize that on this tiny display, we can see that each pixel has a unique value, which we can use essentially as a seed to generate pseudo-random numbers for that pixel. So let's make a function called randomValue, which takes in this initial seed and transforms it in some way. I'll need to look up a good way to do this, but let's just play around a bit first for fun. So how about we multiply the seed by some large number, and then maybe square the result? I really haven't thought this through at all, but I'm thinking that these huge values will overflow the 32-bit integer, and hopefully the remainders will be kind of all over the place and appear random. To try it out, let's divide the result by around 4.2 billion, which is the maximum unsigned integer value, so it'll scale the result down between 0 and 1, and then we can just output our pseudo-random numbers. Let's see how it looks. Okay, well, that's not very convincing. We got a funky looking pattern at least though, so I'll quickly try multiplying by some different values, because I'm curious to see what other kinds of patterns we can make. Alright, I've been randomly trying some different things behind the scenes, and my latest attempt was to multiply the seed by itself a couple of times, but with some random offsets added, and the output from that actually does look reasonably random, I'd say. So now, to generate multiple values per pixel, we can just add this in-out argument type here, which just means that whatever change we make to the seed will be applied to the original value over here. So each time we call it, we should get a different result, and we can visualize that with a random color. Okay, I've had fun playing around with this, but let's get back on track, and I'll replace our little experimental function with some code I found online, which has had a lot more thought and testing put into it. Alright, with random numbers out of the way, we need to figure out random directions, which is the same thing as generating random points on the surface of a sphere. The approach I'm using at the moment is super simple. It just generates 3 random values scaled between -1 and +1, so it's a point inside of a cube. And it just keeps generating these cube points until we get one that is inside of a sphere, which should be around half the time on average. And then we can just normalize that to get our random direction. Unfortunately, whenever there's a while true loop like this, I seem to find a way to get stuck inside of it. Usually this just causes some crashes and random black rectangles on my screen, but today I guess it just stopped bothering to clear the screen between frames, which was an interesting effect. Anyway, after forcing the computer to restart, things were back to normal, and I tracked down the bug and also added a limit to the number of loops just to be safe. I was curious then though to see just how bad it would look if we actually removed the loops and just used the first random point we generated. So I tested that with 50,000 random points, and as you can see they do clump up quite a lot near where the corners and edges of the cube would be, so let's not do that. I then wanted to test another approach I've come across though, which is instead of using uniform random numbers where every value has an equal chance of appearing, we use random numbers in a normal distribution, which looks like this. Here's some code I found for doing that. And now, if we use the values from there to generate our random point instead, then for maths reasons I haven't yet grasped on account of not being a good probabilist, but this here is apparently the reason, our points will be distributed uniformly randomly over the surface of the sphere. On my computer at least, this approach was quite a bit faster for the GPU to compute, and I'm sure there are even faster methods out there, but let's go with this for now. So with random directions working, we need to consider now that when a ray hits a surface, we're actually going to want to pick a random direction in this hemisphere, oriented around the normal vector of the surface. So imagine we generate a random direction and it's rudely pointing outside of the desired hemisphere. A simple way we can detect and fix this is to just take the dot product between the normal vector and the random direction, and that will be negative if they're more than 90 degrees apart. So if it's negative, we can invert the random direction, and just like that, we're back in the right hemisphere. So here's a tiny function for doing that, and here's a quick little test I made just to verify that this really does do what we're expecting it to do. Okay, I think we're finally ready to integrate all the stuff we've been working on into our ray tracer. So I've started by creating this little function, which takes in our ray coming from the camera, and traces its path as it bounces randomly through the scene, and hopefully reaches a light source. How this works is super simple. We just look to see what the ray will collide with using that function from earlier, and if it hits something, then we move the ray to be positioned at the point of intersection, and pick a random direction for the ray to bounce off in. That then keeps repeating until either the maximum bounce limit is reached, or the ray misses everything and shoots off into empty space, in which case we can break out of the loop early. Now, we still need to figure out how much light will actually be received by the camera from all this, so let's create a variable called the ray color, which starts out as pure white. Then, whenever the ray hits something, we can look up its material and simply multiply the ray color by the object's color. So as an example, in the real world, if a particular object absorbs all visible wavelengths of light, then it will appear black. And similarly, if we've defined that the object should appear black in its material, then the ray color will be multiplied by 0, which is like all the light has been absorbed. Okay, so the ray color keeps track of how the incoming light will be affected by the objects it interacts with, but we don't know from the outset what light sources, if any, actually lie along the path of this ray. So let's create another variable to keep track of the light that we encounter, and that just starts out at 0. Then when we hit an object now, let's first calculate how much light that object is emitting, using these emission color and strength properties that I've added to the material. Most objects don't emit light, so this will typically be 0, but if the object is a light source, we can add that emitted light to the total incoming light, and tint it based on the color of all the objects the ray has encountered so far. At the end of all of this, we can just return whatever light we've accumulated along the path. This would be more intuitive if we weren't doing everything backwards, but hopefully that still makes sense. Anyway, the core of our shader now looks like this. We calculate a seed for generating random numbers, then we create a ray looking out from the camera, and finally we trace the path of that ray through the scene to figure out the color of the pixel. Okay, so to test this, I've set up a super simple scene here with just a bunch of little balls sitting on top of one very big ball. Alright, let me grab our settings window here quickly so we can enable ray tracing. And look at that, a photorealistic rendering of a room without any light. But okay, let me try select one of these balls in the dark, and I'm going to duplicate it and then open up its material properties because I want to turn it into a light source. So let's set the color to black because we don't need it reflecting any light, only emitting. So let's then raise the emission strength here, and we can start to make out some pixels of our scene at least. I'll move this glowing orb far away and scale it up, and maybe a bit more, so that it's kind of like a sun. Alright, good night everyone, and back to work. At the moment over here I have the bounce limit set to 1, so the ray from the camera has to hit an object and then bounce directly into a light in order for that pixel to be illuminated. But let's try raising the limit to 2, and we can see the backsides of these spheres are now able to receive some indirect illumination. Each additional bounce is going to have less and less effect though, so for example I'll crank this up all the way to 30, and we can see the difference is pretty subtle. The main problem we have now is that our image is extremely noisy, which is something I'd like to address, but unfortunately my seat has been stolen. The issue though is that we're only sending out a single ray per pixel, but really we need to be sending out as many as possible, letting them all bounce around on their own random paths, and then averaging their contributions to get a better estimate of how much light is really reaching the camera. So I've modified our shader to just loop a bunch of times and add up all the incoming light calculated by the trace function. Then at the end, it just outputs the average. So let's take our single ray per pixel and dial that all the way up to 100. That's certainly looking a lot better than just a single ray, but the image is still quite noisy. Of course, we could set the number of rays even higher, but if we take a quick look at the performance of this, it's already struggling to reach even 60 frames per second, which is a bit pitiful for just a handful of spheres. For today at least though, I am not aiming to have this all running in real time, I just don't want to slow down the editor too much because that's not very pleasant to work with. So let's keep the number of rays per pixel low, but average the result over multiple frames so that the quality gets better with time. That's as simple as taking whatever was displayed on the previous frame and the new render and combining them like this. Obviously, we want the rays to bounce differently on each frame then, so we'll also need to modify our random number seed so that it changes with each frame. And I don't know a particularly good way of doing this, so I'm just going to add the current frame number to the pixel index, but multiply it by some big number and hope for the best. Let's try it out, and okay, clearly we can't have objects moving every frame now or it turns into a smudgy mess, but conceptually it seems to be working at least. I'll test it properly in a second, but I just quickly want to modify our trace function so that when array misses everything, instead of just going out into the void, it gathers some kind of background environment lighting. So I've made this simple function that just blends between a ground color and two sky colors based on the vertical axis of the ray direction, and it also adds in a little circle for the sun based on a given light direction. Here's what it looks like in the scene, so really nothing fancy, but it's a bit nicer than the nothingness we had before, I think. We can change the sun direction like this, by the way, and at some point I'd like to integrate the atmosphere rendering from one of my previous videos so that we could get sunsets and so on, but this will have to do for now. Okay, let's try rendering this little scene, and we can see how over time the image becomes less noisy. I'm not quite happy with how it looks yet though, so let's think a bit more about what happens when our ray hits a surface. Currently, the rays are bouncing off in random directions to see if they reach a light source. Or if we consider this from reality's perspective rather, light is coming in potentially from all directions, and we're trying to estimate how much of that is going to randomly bounce towards the camera. But here's something we haven't considered yet. Imagine a beam of light coming straight down onto the surface from above. We can see that that light covers this little portion of the surface over here. Now imagine the same beam of light, but coming in at an angle to the surface. Clearly, that beam is going to be more spread out, meaning the overall light received by any one point on the surface will be weaker, and so it should contribute less to the lighting of that pixel. So let's go back into our trace function, and we can calculate the strength of the light as the cosine of the angle between the surface normal and the direction towards the light. Then let's multiply the ray color by the light strength, and overall this is going to halve the amount of light that's received. So just as a quick hack to keep the brightness the same for comparison's sake, I'll multiply this by 2. Alright, so here's a render of the balls before this cosine weighting, and here's what it looks like now, which I think is a lot nicer. Let's also quickly see how it looks with the built-in renderer, which obviously is not a fair comparison because not only was this rendered in a fraction of the time, but also there's a bunch of stuff we could do to improve it. The point though is to just help us appreciate some of the things our ray tracer is doing, which we might otherwise take for granted. For example, I really like this bit of extra darkness we're getting beneath the spheres, which really makes them look like they're physically touching the ground. Or another nice detail is this area of red light that we can faintly see bouncing off the white ball here. Anyway, I quickly want to go back to our trace function because through some maths that I don't understand, it turns out that we can remove this light strength calculation we just added if we instead make a small tweak to how we calculate the random bounce directions, like so. This change means that instead of the bounce directions being uniformly distributed over the hemisphere, we have what's called a cosine-weighted distribution. This will send fewer rays in directions that contribute less light, and consequently more rays in directions that contribute more light. So in the end, this gives us the same result as when we're applying that light strength calculation, we just get there a bit faster. Alright, I reckon we've spent enough time looking at these balls, so let's move on to triangles. Here's some code for calculating the intersection of a ray with a triangle, and now prepare to feast your eyes on this beauteous creation. Okay, maybe it doesn't look all that exciting, but of course from the humble triangle we can build pretty much whatever we want. So what should we make? Well, I love the shape of this little chess horsey, so I've been doing my best to model a low poly version of it in Blender. This is made from just 456 triangles, but even that's probably going to be quite taxing on our little ray tracer. We'll have to see. First though, I've added this buffer to the shader for holding all the triangles in the scene, and then there's also a buffer to store information about each mesh, which mainly just tells us where in the big triangle list a particular mesh begins, and how many triangles it contains. Finally, I've added this bit of code to the ray collision function, which is essentially identical to how we handled the spheres, simply testing if the ray hits any of the triangles, and storing the information about the closest one if it does. Before looking at all the triangles though, it does quickly test if the ray intersects the object's bounding box, just to optimize things a tiny bit at least. Alright, I'm going to set up a simple test scene here quickly, something along the lines of the classic Cornell box, so basically just a little room with walls of different colors. Then let's bring in the night, and I'll give it a plain white color so we can see how it interacts with the colors of the room. Unfortunately, I can already tell that the editor is lagging quite a lot from my inefficient ray tracing code, so let's just drop the number of rays all the way down to 1 per pixel. I'll need to try optimize this at some point, but let's just put up with the noise for now. To finish this off, I'm going to add in a front wall so that the room is completely enclosed, and I'll use a quad mesh for this instead of a cube, just so that it's invisible from the backside, allowing us to still see into the room. Of course, the room is now completely dark, so that's not much use, and I guess we might as well turn off the sun now, but then let's duplicate the ceiling, scale it down a little bit, and use that as our light source instead. Okay, let's let this render for a bit, and we can see our majestic night gradually emerging from the noise. You can also see some nice bounce lighting with this red tint along the one side here, and the bluish shading on the other side, and even some green under here and along the base coming from the floor. Just for interest's sake, here's what it looks like if we only allow the light to bounce once. Then here's with 2 bounces, and here's back to our original image with 10. I'd like to try this out with another model quickly, so I'm going to bring in Suzanne the Blender Monkey to pose for us. This is excruciatingly laggy though, so I'll disable our ray tracer while we set up the scene here, and then let's see how it looks. That's looking pretty good, but I know what you're thinking. What if Suzanne were to enter the avatar state and light the room with her glowing eyeballs? Well, there you go. Behind the scenes, I've been trying to optimize the rendering a bit, and I actually did manage to speed things up dramatically. The only downside is that Suzanne now looks like this. I'm a bit torn because it really is a lot faster, but I think I'm going to have to revert my changes. Anyway, let's move on to Specular Reflections, which remember is when we have a very smooth surface like a mirror, so light bounces off it perfectly with the same angle going out as it had coming in. This perfect reflection can be calculated based on the normal vector and the incoming direction, like this. So in our trace function, we're calculating the diffuse direction over here, and instead of always using that for the new ray direction, let's now also calculate the specular direction using this built-in reflect function. Then the ray's new direction can blend from the diffuse direction to the specular direction based on this smoothness property that I've added to the material. So let's try it out. I've placed a few spheres in our little test chamber here, and let's just see how that looks at the moment. Alright, now let's make these balls shiny. So I'll set the smoothness on the first one to around 0.4, then the next one maybe 0.6, then 0.8, and the last one can go all the way up to 1. So here's what we had before, and now with our new specular reflections. As we'd expect, this goes from very blurry reflections on the left, since it has a low smoothness value, to a nice crisp mirror on the right. I'd like to play with this a little bit more, so I've set up a similar scene here, this time with just 2 big balls though, and I'm going to make them both fully reflective. Since they're opposite one another, we can see the other ball reflected in this ball, and that reflection of the other ball of course contains a reflection of this ball, and so on. So let's render that, and I've animated the balls to move forwards until they're just touching one another, giving us some nice infinite reflections. I want to try one last reflection test with our little horse here quickly. Here's what the scene looks like at the moment, which is pretty dull, so let's spice it up by making this wall here be a mirror. Alright, let's then make the wall opposite it reflective as well, and I'll give it a smoothness of just less than 1, so that things get slightly blurrier with each reflection, which I think looks nice. But why stop there? Let's make the red wall reflective, and the blue wall too. next the ceiling, and the floor. Finally, we might as well make the horse reflective too. Truly one of the artworks of all time. Anyway, what's going on with this tomato? The tomato is red, but the specular highlights we see on it are white, or rather, they're the color of the light that's hitting it and bouncing specularly into the camera. But in our ray tracer, if we take a red object and make it shiny, we can see that the specular highlights are tinted red, which seems intuitive. So what's going on with the tomato? Well, it turns out that fruits have a transparent protective coating, and when light hits that, some of it will go through and be scattered diffusely, but some amount of light will also bounce off the smooth coating, giving us those untinted reflections. And the same idea applies to many other materials, such as varnished wood, for example. So in our trace function, let's figure out if the current ray should be bouncing off some imaginary coating by taking this specular probability that I've added to the material and testing if it's greater than a random value between 0 and 1. Then let's just make sure that the diffuse direction gets used if this is not a specular bounce, and we can also use this information to select between either the material's regular color or its specular color, which we'll probably just leave white most of the time. To see what this looks like, I'm going to take these 4 balls from earlier and make them all totally smooth. But we're now able to say that that smoothness should only apply some of the time, so I've set up some probabilities, and let's see how that turns out. I'd say that's looking pretty good, but for the real test, let's try it out on our tomato ball. At the moment it looks like some strange kind of metal, I guess, but now using our new settings, we're able to make something like this, which definitely feels a lot more tomato-y. Okay, now there are still so many things I want to experiment with, but let's end off today with just one last effect, which is depth of field. The basic idea here is that we're able to choose a distance at which things appear in focus, and outside of that distance, things will be blurry. So let's go all the way back to the beginning, where we were calculating the direction of the rays for each pixel, and just focus in for a moment on a single pixel. We are actually now sending out multiple rays per pixel, but they're all starting from the same position and going in the same direction, so it just looks like a single ray. To make things blurry then, all we need to do is make the rays diverge a little bit, so that they're all heading out in slightly different directions. So over in the code where we're sending out all the rays for the current pixel, let's grab the ray setup code and move it inside the loop so that we can make each one slightly different, which we can do simply by randomly nudging this viewpoint. To do that, I want to generate a random point inside of a circle. So here's a little function that begins by calculating a random angle, and then converts that to a point on the unit circle using sine and cosine. Finally, that gets scaled down by the square root of a random value to be somewhere inside the circle. The square root might seem a little mysterious at first, but without that we can see that the random points cluster towards the center of the circle, so the square root just ensures that they spread out nicely. Anyway, let's now take that random vector and multiply it by the strength setting I've added. Then using that, we can make a new viewpoint that lies somewhere inside a circle around the original viewpoint, and let's plug that into our direction calculation here. Okay, that is not working at all. Apparently I'm just making up variables that don't exist at this point, so after consulting the matrix documentation, because I always forget the syntax for accessing the different rows and columns, I've extracted the missing camera directions that we used for offsetting the viewpoint, so the code should actually compile now. Alright, I've set up this little test scene, and let's try increasing the size of that random circle using this strength setting here. That does seem to be making things blurry, but it's also extremely noisy as usual, so let's render it quickly. Of course, this does make everything blurry and we can't focus on anything, so we'll need to make some adjustments, but it's a start at least. And actually, if we turn this off quickly, something that it could already help us with is these jaggedy edges our image has, which is simply due to the limited number of pixels in the screen. So if we just set the blur strength extremely low, that'll help to smooth out these harsh edges, giving us some nice anti-aliasing. Here's a little render I made to test this, and I'd say the edges are looking pretty smooth. Okay, so we can make things blurry if we want, but we still need to figure out how to focus at a particular distance. So what if, instead of randomly offsetting this viewpoint, we randomly offset the ray origin? That'd give us something like this, where the rays now all converge on the viewpoint. So if we have some model and we bring that over here, the rays will be hitting it at a bunch of different spots, giving a blurry result for the current pixel. But if the model moves a bit further back, then all the rays will be hitting the same point, and so it'll be in focus. Of course, the rays don't just stop at this plane, they extend out potentially forever, and so if the model were to move even further back, past this focal plane, I guess we could call it now, then it will start getting blurry again. So to control what's in focus here, we can simply adjust the distance of the plane. Back in the code, let's keep our old approach since it's helpful for anti-aliasing, and we can just calculate another random vector using our point in circle function again, and then use that to offset the ray origin. That's actually all we need to do, I think, because changing the focus distance is already handled by the z component of these view parameters. So to test this, I've set up a slightly larger scene here, and let's just play around a bit. To begin with, I'll try setting the defocus strength to 2, which doesn't seem to have done much, so let's try 20, or maybe even 200. Okay, that's made everything super blurry, so let's play with the focus distance now. I'll turn on this visualization I added behind the scenes, and let's just try shifting this plane all the way back to the same depth as the night. As we'd expect, the night seems to be pretty sharp, whereas these pawns in the foreground here are still very out of focus. I'd like to see this with a bit less noise, so I'm going to temporarily crank the number of rays up from 3 to 30, and my computer is dying, but I think it looks nice. Okay, I'll turn that back down again, and let's try bringing the foreground into focus now. And let's also see how that looks with some more rays. This seems to be working quite well, so I'll just do one last render to test it. Here we have the king and queen in focus, and now I'll animate the focus plane shifting out to highlight the night. Alright, there's still so many things I want to do, for example rendering objects made from glass, adding volumetric effects, and of course improving the performance so we can experiment with slightly more complex scenes. But we've covered a lot of ground already, so let's leave it here for today and perhaps tackle those topics in the future. Okay, I hope you enjoyed the video, and until next time, cheers.